Hello and welcome to Sleepy Engineering. In this video, we will explore the concept, calculation, and application of gear ratios in excruciating detail. Gears are essential components in countless machines, from simple clocks to complex transmission systems, and understanding how gear ratios work is fundamental to mechanical engineering. This narration is intentionally slow, detailed, and repetitive. It is designed to help you relax, focus, or fall asleep. There will be no sudden sounds, no music, and no emotional tone, only the steady voice of information. Now please sit back, close your eyes if you like, and let the story of gear ratios begin. Gears are one of the oldest and most essential mechanical components in engineering, serving as the foundation for the transmission of motion and force between rotating elements. Their presence is deeply integrated into the machinery of human civilization, from ancient timekeeping devices to the inner workings of modern vehicles and robotic arms. At their most basic level, gears are circular tools with evenly spaced teeth cut around their edges, designed to mesh with the teeth of other gears. When one gear rotates, it transfers motion to the next through the interlocking of these teeth, creating a controlled and predictable mechanical response. This interaction is the essence of mechanical advantage. The purpose of gears is to manipulate the force and speed of rotational motion in ways that suit the intended function of a system. Mechanical advantage is achieved by altering the relationship between the input and output speeds and torques through the ratio of gear sizes. If a large gear drives a smaller gear, the smaller gear will rotate faster but with less torque. Conversely, if a small gear drives a larger one, the result is a slower rotation, but with greater torque. This relationship is fundamental to the operation of everything from bicycles to industrial gearboxes. Gears allow engineers to tailor machines to perform specific tasks with precision and reliability. They are commonly made from durable materials such as steel, bronze, or engineered plastics, and their tooth profiles are carefully designed to reduce friction, distribute load evenly, and ensure long-term durability. The most common gear shape is the spur gear, which has straight teeth and is used in parallel shaft applications. Other types include helical gears, bevel gears, worm gears, and planetary gear systems, each chosen based on the direction of motion, load requirements, and spatial constraints. The origin of gear use can be traced back thousands of years to ancient civilizations that employed primitive gear mechanisms in water lifting devices and astronomical instruments. Over centuries, the study of gears evolved into a refined science, with contributions from notable thinkers and engineers, leading to the development of precise gear theory, manufacturing techniques, and standards. In modern engineering, gears are not only physical objects, but also elements of mathematical design, simulated in software before being manufactured with precision tools. Understanding how gears function requires familiarity with concepts such as pitch diameter, module, pressure angle, and backlash. These parameters influence how well gears mesh, how much noise and vibration they produce, and how efficiently they transfer power. Gear design is a balance between strength, efficiency, size, and cost. Engineers must consider the environment in which the gears will operate, including temperature, lubrication, and exposure to contaminants. For example, gears used in space exploration must endure extreme temperatures and vacuum conditions, while gears in food processing machinery must resist corrosion and meet sanitary standards. Mechanical advantage gained through gears is not only about power, it is also about control. In systems where precise motion is required, such as in clocks or CNC machines, the correct gear ratio ensures that each movement is exact and repeatable. Gear systems can be simple, involving 2 meshing gears, or complex, involving dozens of interconnected elements. Regardless of complexity, the underlying principles remain the same. Energy is transferred from one rotating body to another through mechanical contact, and this transfer is governed by the geometry and arrangement of the gears. The importance of gears in daily life often goes unnoticed. From the power window motors in cars, to the rotors in washing machines, and the turbines in power plants, gear mechanisms are working silently in the background. Their efficiency and reliability make them indispensable in almost every field of engineering. As we begin this deep dive into gear ratios, it is essential to appreciate the role gears play, not just as components, but as systems that define how machines behave. The choice of gear type, size, and configuration has a direct effect on a machine's performance, energy consumption, and durability. Each decision in gear selection is rooted in mechanical reasoning and practical constraints. The process of designing a gear system starts with understanding the application requirements, such as desired output, speed, torque, and direction of motion. From there, engineers calculate the gear ratio needed to achieve those targets. This ratio defines how many times the input gear must turn to produce a single turn of the output gear. The simplicity of this concept is deceptive, as it underlies some of the most sophisticated machinery ever built. In the following sections, we will explore gear ratios in exacting detail, examining how they are calculated, applied, and optimized in various engineering contexts. We will investigate the mathematical relationships, mechanical considerations, and real-world implications of using different gear configurations. Through this journey, the true depth and elegance of gear mechanics will become clear, revealing why such seemingly simple components hold such profound importance in the world of machines. Gear ratios are at the heart of mechanical systems that rely on rotational motion. At its most basic level, a gear ratio is a comparison between the number of teeth on 2 meshing gears, or the number of rotations each gear makes in relation to the other. When 2 gears are connected, one gear drives the other, and the relationship between their sizes determines how fast and how forcefully the second gear moves. This relationship is known as the gear ratio. If a small gear with 10 teeth drives a larger gear with 20 teeth, the gear ratio is 1:2. This means that for every 1 revolution of the smaller gear, the larger gear turns only half as much. The concept can be extended to many gear pairs and to more complex systems, such as gear trains and transmissions, but the underlying principle remains consistent. The gear ratio tells us how the input motion will be transformed into output motion. It affects speed, torque, and direction of rotation. A higher gear ratio reduces speed but increases torque, while a lower gear ratio increases speed but reduces torque. This inverse relationship is crucial in mechanical systems, where both power and precision are required. Consider a bicycle as a simple and familiar example. When the cyclist pedals, the front chainring turns, pulling the chain and rotating the rear sprocket. The size difference between these two gears determines how much force is transferred to the wheel and how fast the bicycle moves. A small chainring with a large rear sprocket results in easy pedaling and more torque, useful for climbing hills. A large chainring with a small rear sprocket increases speed but requires more effort. This practical application of gear ratios illustrates how engineers design machines to meet specific needs. In automotive transmissions, for instance, first gear usually has a high ratio, meaning the engine turns several times for every turn of the wheels, giving high torque for starting. Higher gears reduce the ratio and allow for higher speeds at lower engine revolutions. Gear ratios also determine the efficiency and effectiveness of machines. If the gear ratio is not appropriately selected, the system may underperform or even fail. Engineers must consider not only the size of the gears, but also the number of teeth, the pitch diameter, and the alignment to ensure smooth operation. Another important aspect of gear ratios is their reversibility. In a gear pair, when the driver gear moves clockwise, the driven gear moves counterclockwise. This change in direction is consistent unless an idler gear is added between them. The gear ratio, however, remains unaffected by the presence of an idler. The number of teeth on each gear is what governs the ratio, not the direction. To calculate a gear ratio, one can divide the number of teeth on the driven gear by the number of teeth on the driver gear. This simple division provides a numerical value that describes how many times the input gear must turn to make the output gear complete one rotation. If the driven gear has 40 teeth and the driver has 10, the gear ratio is 4:1. This means the driver must rotate 4 times to move the driven gear once. The concept of gear ratios extends beyond simple gear pairs. In compound gear trains, where multiple gears are used in sequence, the total gear ratio is the product of the individual ratios. This allows for fine-tuned control of speed and torque. Engineers use this principle to design everything from robotic arms to mechanical clocks. In these systems, gear ratios must be carefully calculated and matched to the application's requirements. For example, a clock mechanism needs precise gear ratios to translate the movement of the escapement into accurate motion of the hour, minute, and second hands. Understanding gear ratios also requires an appreciation of the trade-offs involved. Increasing torque through a high gear ratio means sacrificing speed, and vice versa. This trade-off is governed by the conservation of energy. No gear system can create energy. It can only transform it. By increasing torque, we are spreading the same energy over a longer period or distance, thereby reducing speed. This is why large vehicles like trucks use high gear ratios when pulling heavy loads. They need torque more than speed. Conversely, sports cars use low gear ratios for quick acceleration. In mechanical design, selecting the right gear ratio involves balancing multiple factors, including the load, speed, efficiency, and space constraints. In summary, gear ratios are more than just numbers. They are the foundation of mechanical transmission. They determine how forces are transferred and transformed within a machine. They define the performance of engines, the efficiency of tools, and the motion of everyday mechanisms. By grasping the basic concept of gear ratios, one begins to understand the invisible forces that make machines work. This understanding is essential not only for engineers, but for anyone interested in the mechanics of motion. Understanding the foundational relationship between torque, speed, and force is essential in comprehending how gear ratios work within mechanical systems. Torque is the rotational equivalent of linear force and is measured as the product of a force and the distance from the axis of rotation. This distance is often referred to as the moment arm, and the longer the moment arm, the greater the torque generated for a given force. Torque is what allows wheels to turn, levers to lift, and engines to transmit power through drive shafts. It is the fundamental quantity responsible for causing angular acceleration in rotating bodies. Speed in a rotational context is often referred to as angular velocity, which measures how fast an object is spinning or rotating around an axis. This is typically measured in revolutions per minute or radians per second, and it tells us how quickly something is rotating, without necessarily indicating how much force or power is being transmitted. When discussing gear ratios, the concept of speed is inseparably linked to torque, since a change in one usually results in an opposite change in the other, due to the conservation of energy. The product of torque and rotational speed in consistent units gives us power, which is the rate at which work is performed. This relationship can be expressed mathematically as power equals torque, multiplied by angular velocity, and this equation is central to understanding how energy is managed in mechanical systems. Force is the linear interaction that causes an object to accelerate or deform, and when force is applied at a distance from a pivot point, it generates torque. The distinction between linear force and torque is critical, because it explains why using a wrench with a longer handle allows more torque to be applied without increasing the amount of force exerted. The longer handle increases the moment arm, thus amplifying the torque with the same applied effort. In the context of gears, these principles manifest in the transfer of energy between rotating components. If a small gear drives a larger gear, the torque increases while the speed decreases. This is known as mechanical advantage, and it allows machines to trade speed for force or vice versa, depending on the requirements of the task. This trade-off is fundamental to all gear systems and can be observed in everyday tools, such as bicycles, where changing the gear ratio allows a rider to pedal more easily up a hill by increasing torque and reducing speed, or to accelerate on a flat surface by decreasing torque and increasing speed. In automotive transmissions, these concepts allow engines to operate efficiently at different speeds and loads by altering the gear ratios to match the driving conditions. Higher gears provide less torque but greater speed, while lower gears provide more torque and less speed. This dynamic balance is essential to performance efficiency and fuel economy. Another important aspect of torque, speed, and force is their directionality. In gear systems, direction of rotation can be reversed depending on how gears are arranged. For instance, when two gears mesh directly, they rotate in opposite directions. But if an idler gear is placed between them, they rotate in the same direction. Understanding this allows engineers to design complex systems where directional control is as important as speed and torque. Output torque in gear systems is not just a function of input torque and gear ratio, but also depends on system losses, such as friction and backlash, which reduce the efficiency of power transmission. These losses must be considered in real-world applications because they impact the actual torque delivered to the output shaft. Additionally, gear tooth geometry and material properties affect the ability of a gear system to transmit force reliably. without wear, slippage, or failure. When gears are designed for high torque transmission, they are often made from hardened steel with optimized tooth profiles to distribute load evenly and minimize stress concentrations. This ensures that the gears can handle the required forces without mechanical degradation over time. The concept of torque multiplication is particularly useful in heavy machinery, such as cranes and winches, where small motors can lift heavy loads by employing high reduction gear ratios to significantly increase output torque, even if the rotational speed is reduced to a crawl. This application underscores the power of mechanical systems to convert energy in ways that maximize utility in specific contexts. Torque, speed, and force are also foundational in robotics, where actuators must deliver precise amounts of torque to achieve controlled movements. Speed reduction through gears enables greater control over joint positions and movement smoothness, which is critical in applications like surgical robots or manufacturing arms, where accuracy is paramount. In summary, the interrelationship between torque, speed, and force forms the cornerstone of mechanical engineering principles, governing motion control and power transmission. These concepts are not isolated, but rather interconnected in a dynamic equilibrium, where changes in one quantity invariably influence the others. Gears, pulleys, and levers all function by exploiting this balance to perform useful work with efficiency and reliability. Mastery of these fundamentals enables engineers to design systems that are both powerful and precise, capable of functioning across a wide range of applications, from delicate instruments to industrial machinery. A simple gear train consists of 2 or more gears connected in such a way that motion and torque can be transferred from one gear to another through direct contact of their teeth. This concept is fundamental in mechanical engineering, as it allows machines to transmit power, change speed and direction of rotation, and alter the torque applied to mechanical loads. The simplest gear train involves a driving gear, known as the input gear, and a driven gear, known as the output gear. These 2 gears are mounted on separate shafts, and the teeth of the driving gear push against the teeth of the driven gear, causing it to rotate in the opposite direction. If the driving gear has more teeth than the driven gear, the gear ratio is less than 1, which results in a speed increase, but a decrease in torque. Conversely, if the driving gear has fewer teeth than the driven gear, the gear ratio is greater than 1, and this produces a speed reduction, but an increase in torque. The gear ratio of a simple gear train is calculated by dividing the number of teeth on the output gear by the number of teeth on the input gear. This ratio determines how many revolutions the input gear must complete for the output gear to make one full rotation. For example, if the input gear has 10 teeth and the output gear has 20, the ratio is 2, and the output gear will rotate once for every 2 turns of the input gear. This is referred to as a 2-to-1 gear reduction, and it illustrates how rotational speed and torque are inversely related in gear trains. If an additional gear is placed between the input and output gears, it is referred to as an idler gear. The purpose of an idler gear is not to change the gear ratio, but rather to reverse the direction of rotation of the output gear so that it rotates in the same direction as the input gear. The idler gear also allows the distance between the input and output shafts to be adjusted while still maintaining a connection between them. Importantly, the inclusion of an idler gear does not alter the overall gear ratio of the system, because its only function is to transfer motion. The behavior of simple gear trains can be analyzed using rotational kinematics and the conservation of energy. Since energy cannot be created or destroyed in a mechanical system, the power input must equal the power output, minus losses due to friction and other inefficiencies. In idealized systems with no friction, the product of torque and angular velocity remains constant throughout the gear train. As a result, if speed is increased, torque must decrease, and if torque is increased, speed must decrease. The direction of rotation is another important aspect of gear behavior. When two gears mesh directly, they rotate in opposite directions. This can be useful in applications where a reversal of motion is desired or must be accounted for. In cases where the output must rotate in the same direction as the input, an even number of gears must be used so that each change in direction is reversed again, resulting in matching rotational direction. Gear teeth are designed to mesh smoothly and transmit forces efficiently. The most common tooth profile is the involute curve, which ensures that the gears maintain constant velocity ratio during rotation. This consistent motion transmission is essential for applications requiring precision, such as clocks, instruments, and control systems. When gears are used in series within a simple gear train, each gear in the series influences the behavior of the next. For example, if a small input gear drives a large gear, which then drives another small gear, the final output will reflect the cumulative gear ratio of the entire sequence. The total gear ratio of a gear train is determined by multiplying the individual ratios of each pair of meshing gears. This principle allows for complex control over speed and torque using only simple mechanical components. In real applications, gear trains must account for backlash, which is the slight movement that occurs between gear teeth when direction is reversed. Backlash results from the necessary clearances between gear teeth to prevent binding and wear. It can cause inaccuracies in positioning systems and must be minimized in applications like robotics and CNC machinery, where precise control is critical. Materials used in gears also affect their performance and behavior. Steel is common for high-strength applications, while plastic gears are used for low-load or quiet operation situations. The type of lubrication used can significantly affect gear train efficiency by reducing friction and wear. Heat buildup in gear systems is another consideration, especially at high speeds or under heavy loads. Cooling mechanisms or specific materials may be used to mitigate thermal expansion and maintain consistent performance. In some, simple gear trains offer a reliable and versatile method of power transmission. They embody the fundamental principles of mechanical advantage, torque, speed, and energy conservation. Understanding their behavior enables engineers to design machines that operate efficiently and predictably in a wide range of applications, from basic tools to complex industrial machinery. In mechanical engineering, gear trains are systems where multiple gears are arranged in sequence so that their rotational energy is transmitted from one shaft to another, often with changes in speed or torque. The basic principle behind gear trains is the continuous meshing of gear teeth, which allows for a smooth and controlled transfer of mechanical power through rotation. When two gears mesh, the driving gear imparts rotational motion to the driven gear, and the ratio between their number of teeth determines the resulting speed and torque. A gear train allows engineers to expand upon this basic interaction by introducing intermediate gears, commonly referred to as idlers, or by arranging multiple gear pairs in a single system to achieve a specific mechanical advantage. In compound gear systems, one shaft contains two gears of different diameters, rigidly fixed together. These compound gears engage with other gears in the system, and this configuration allows for a larger range of speed reductions or increases within a relatively compact space. This design is essential in machinery where space is limited, but a significant change in output speed or torque is necessary. Compound gear trains are commonly used in applications such as clocks, gearboxes, robotics, and various types of machinery where precision and compactness are required. When analysing gear trains, it is important to consider the overall gear ratio of the system. The gear ratio is determined by multiplying the individual gear ratios of each meshing pair in the train. The overall gear ratio affects the output speed and torque relative to the input, and engineers use this value to ensure that the machine performs as intended. The direction of rotation must also be considered, as each meshing pair inverts the direction of rotation. For instance, if a simple gear train consists of 3 gears, the final gear will rotate in the same direction as the first. This behavior is useful in designing machines where the direction of movement must be preserved or reversed based on the requirements of the task. Efficiency in gear trains depends on factors such as the number of gears, the precision of the gear teeth, the type of lubrication used, and the alignment of the shafts. Each additional gear in the system introduces more points of potential energy loss due to friction and backlash, which refers to the small gap between mating gear teeth that can lead to play or slop in the system. To minimize these losses, high-precision gears are often used, and the entire gear assembly is housed in a rigid frame to prevent misalignment during operation. In compound gear trains, engineers must also consider the arrangement of the gears in terms of center distances and shaft layout. Vertical, horizontal, or angled configurations are chosen based on the intended use and space constraints. Timing and synchronization are also crucial, particularly in systems such as printing presses or automated manufacturing lines, where the slightest deviation in gear timing could result in defective products or damaged machinery. Spur gears are the most common type used in basic gear trains due to their simplicity and ease of manufacturing. However, in compound gear systems, engineers may also use helical gears, which offer smoother operation and higher load capacity due to the angled teeth. Bevel gears and worm gears can also be integrated into compound gear trains, where changes in axis orientation or high reductions in speed are necessary. These more complex gear types introduce additional considerations, such as axial thrust loads, lubrication needs, and specific material choices to prevent excessive wear. Compound gear systems also provide opportunities for multiple output speeds from a single input, allowing machines to perform various functions without requiring separate motors or drives. This multi-speed capability is achieved through selective engagement of different gears, often via sliding mechanisms or clutches, enabling the operator to switch between configurations depending on the task at hand. In modern mechanical design, compound gear trains are often simulated using computer-aided design software to model stresses, deflections, and performance under various load conditions. This allows for optimized gear layouts before physical prototypes are constructed, saving both time and resources. The gear teeth profiles are designed to conform to standard shapes, such as the involute profile, which ensures consistent power transmission and minimizes wear over time. The combination of theory and simulation enables the production of gear systems that are both reliable and efficient, even under demanding conditions. The materials chosen for gear trains vary depending on the required strength, wear resistance, and cost considerations. Common materials include steel, bronze, cast iron, and high-performance plastics for lighter-duty applications. Surface treatments such as carburizing, nitriding, or induction hardening are applied to gear teeth to extend their lifespan by increasing surface hardness. Lubrication systems may be passive, such as grease, or active, involving oil baths or pressurized lubrication, depending on the speed and load conditions. In sum, gear trains and compound gear systems are vital to mechanical engineering, allowing precise control over speed, torque, and direction of motion. Their design requires an understanding of gear ratios, power transmission, efficiency, and the mechanical behavior of materials under load. These systems are found in everything from automotive transmissions to industrial machinery, and their continued evolution has enabled modern engineering to achieve unprecedented levels of functionality and efficiency in compact spaces. Gear ratios are a foundational concept in mechanical engineering and play a crucial role in the operation of countless machines, from simple bicycles to complex industrial gearboxes. The principle of gear ratios revolves around the relationship between the number of teeth on two meshing gears and how that relationship affects rotational speed and torque. When two gears are in mesh, the gear ratio is defined as the ratio of the number of teeth on the driven gear to the number of teeth on the driving gear. This means that if a gear with 20 teeth drives a gear with 40 teeth, the gear ratio is 2:1, indicating that the driven gear will rotate once for every 2 rotations of the driving gear. This has the effect of reducing speed while increasing torque, making it possible for machinery to perform tasks that require more force at slower speeds. Conversely, when a smaller driven gear is powered by a larger driving gear, the result is an increase in speed and a decrease in torque. This concept is widely utilized in applications where quick movement is more desirable than force output, such as in high-speed machinery or automotive transmissions in higher gears. The essence of gear ratios is that energy is conserved but transformed in form. When torque increases, speed decreases proportionally, and vice versa. Engineers use this relationship to optimize machines for their intended purpose, whether that purpose requires precision, force, speed, or a balance of all three. Gear ratios can be expressed in several ways, including as a fraction, a colon-separated format, or a decimal. Each format provides insight into the mechanical advantage or disadvantage provided by the gear setup. Understanding gear ratios also requires familiarity with gear trains, which are combinations of multiple gears used to achieve a desired output. In compound gear trains, the overall gear ratio is the product of the individual gear ratios in the sequence. For example, if one gear pair has a ratio of 2:1 and the next pair has a ratio of 3:1, the overall gear ratio is 6:1. This compounded effect allows for very large changes in torque or speed within a relatively compact system. Engineers must consider the direction of rotation as well. When two gears mesh directly, they rotate in opposite directions. To maintain the same direction of rotation from input to output, an idler gear may be inserted between the driving and driven gears. While the idler does not affect the gear ratio, it restores the original direction of motion. This becomes important in systems where the orientation of movement matters, such as conveyor systems or robotics. The shape and size of gears also influence the gear ratio. Spur gears, which have straight teeth and are mounted on parallel shafts, are the most basic type. Helical gears have angled teeth and offer smoother and quieter operation. Bevel gears connect shafts at an angle, typically 90 degrees, and are often used in automotive differentials. Worm gears involve a screw-like input that drives a gear at 90 degrees and provide very high gear ratios in a compact form with a self-locking feature that prevents backdriving. Planetary gear systems consist of a central sun gear, multiple planet gears, and an outer ring gear. These arrangements are highly efficient and compact, offering multiple gear ratios within a single system. They are commonly used in automatic transmissions, robotics, and aerospace applications. Calculating gear ratios involves careful measurement and attention to detail. The pitch diameter of a gear, which is the diameter of the circle formed by the contact point of the gear teeth, plays a critical role in determining gear ratios. The number of teeth divided by the diametral pitch provides this diameter and helps ensure that gears mesh properly without excessive backlash or interference. Backlash is the small gap between gear teeth that allows for lubrication and manufacturing tolerances, but too much backlash can result in imprecise motion and noise. Engineers must strike a balance between minimizing backlash and allowing enough space for smooth operation. Proper lubrication and alignment also impact gear performance. Misaligned gears can result in uneven wear, increased friction, and eventual failure. Therefore, accurate gear ratio calculations and meticulous assembly are essential in gear design. Torque transmission through gears is also influenced by material properties. Stronger materials, like hardened steel, can withstand higher loads and transmit more torque without deforming. Lightweight materials like aluminum may be used in applications where weight reduction is a priority, though they may wear out more quickly. The angle of gear teeth, known as pressure angle, typically ranges between 14 and 20 degrees and affects the force distribution along the teeth. A higher pressure angle increases strength, but can also raise friction and noise levels. In addition to mechanical factors, engineers must consider the intended use case. For example, a gearbox designed for industrial machinery may prioritize durability and load capacity, while one for a remote-controlled vehicle may emphasize compact size and responsiveness. Each application dictates different gear ratio requirements and constraints. Moreover, efficiency is a key factor. Every gear interaction introduces some energy loss due to friction. High-efficiency gear trains minimize these losses through optimized design, materials, and lubrication. In critical systems like aircraft or medical devices, efficiency and reliability are paramount and require extensive testing and validation. Gear ratios also influence acceleration and deceleration characteristics. In automotive transmissions, lower gears provide high torque for quick acceleration, while higher gears offer better fuel efficiency at cruising speeds. Continuously variable transmissions use belts and pulleys to provide an infinite number of gear ratios, optimizing engine performance across all speeds. In robotics, gear ratios determine the precision and strength of motion. A robotic arm used in surgery may use high gear ratios to ensure delicate and controlled movements. Conversely, industrial robots on assembly lines may use different ratios for speed and efficiency. Understanding gear ratios allows engineers to harness mechanical energy in the most effective way possible, matching input power to desired output characteristics with precision and control. Now that we have examined the fundamentals and practical applications of gear ratios, we can explore the intricate design elements that allow gears to function with such reliability and versatility across countless industries. In order to fully grasp the mechanical behavior of gear systems, one must understand the concepts of torque and rotational speed and how they are manipulated through gear ratios. Torque is the rotational equivalent of linear force and represents the tendency of a force to cause an object to rotate about an axis. It is calculated as the product of the applied force and the perpendicular distance from the axis of rotation to the point of force application. Rotational speed refers to how fast an object is spinning and is usually measured in revolutions per minute or radians per second. Gear systems allow engineers to trade off torque and rotational speed, depending on the needs of the mechanical application. When a small driving gear engages a larger driven gear, the result is a decrease in speed, but a corresponding increase in torque. This trade-off is governed by the conservation of energy principle, which states that energy cannot be created or destroyed, but only transformed. Therefore, as rotational speed decreases, torque must increase to maintain the same power output, minus any losses due to friction or inefficiencies in the system. Similarly, when a large driving gear turns a smaller driven gear, the rotational speed increases while the torque decreases. This is desirable in systems where rapid motion is needed, but where high torque is not essential. Understanding these trade-offs is fundamental to designing gear systems for specific functions. Engineers often use the equation power equals torque multiplied by rotational speed to calculate the necessary parameters. When adjusting a gear system to handle a certain load or movement requirement, modifying the gear ratio allows precise control over both torque and speed. Torque multiplication is especially important in systems that need to move heavy loads, such as cranes, winches, and elevators. In such applications, a high gear ratio provides the mechanical advantage necessary to lift or move objects with less effort. Conversely, systems that require fast rotation, such as turbines or high-speed cutting tools, benefit from lower gear ratios that increase speed at the expense of torque. Gear ratios also influence the moment of inertia experienced by the system. The moment of inertia is a measure of an object's resistance to changes in rotational motion and depends on the mass distribution relative to the axis of rotation. In gear systems, changing the gear ratio alters the effective moment of inertia experienced at the input shaft. A higher gear ratio increases the reflected inertia, making it feel like the load is heavier or harder to start moving. This effect must be considered in systems requiring precise control or rapid response. Engineers use equivalent inertia formulas to evaluate how gear ratios influence control dynamics and energy consumption. Acceleration and deceleration rates are also affected by gear ratios. A gear system with a high torque multiplication factor may accelerate more slowly due to the increased inertia, but will provide greater control and stopping power. On the other hand, systems geared for high speed may accelerate rapidly, but require more sophisticated braking mechanisms to slow down effectively. These dynamics are particularly important in vehicles, robotics, and automation systems, where precise motion control is essential. Thermal considerations also come into play in gear design. When torque and rotational speed are manipulated through gears, frictional forces generate heat at the points of contact. This heat must be managed to prevent wear, deformation, or failure of the gear teeth. Lubrication systems are employed to reduce friction and carry away heat, while materials are chosen based on their thermal conductivity and resistance to temperature-related degradation. Engineers must also consider the duty cycle of the gear system, which refers to the amount of time the system is under load compared to its rest period. Continuous duty applications require gears that can handle sustained torque and speed without overheating or wearing out prematurely. Load characteristics further influence gear selection. A constant load applies the same force over time, while a variable load changes in magnitude or direction. Shock loads are sudden and extreme, such as those experienced during gear engagement or emergency stops. Gear systems must be designed to absorb and distribute these loads without failure. Torsional vibration is another concern, especially in high-speed applications. When gear systems transmit power, they may experience periodic variations in torque due to tooth engagement and backlash. These variations can cause resonance and vibration, which must be dampened through careful design and material selection. Balancing gears and shafts helps minimize these dynamic effects, improving the longevity and reliability of the system. Engineers also analyze stress distribution across gear teeth using finite element analysis or empirical methods. Contact stress, bending stress, and surface fatigue are critical factors that influence gear lifespan. Proper tooth profile design, surface treatment, and load distribution strategies are used to mitigate these stresses and ensure consistent performance. Efficiency losses in gear systems typically range between 1 and 5% per mesh, depending on gear type, alignment, lubrication, and speed. Spur gears, while simple and easy to manufacture, can be less efficient than helical or bevel gears in certain configurations. Worm gears, though compact and capable of high reduction ratios, often suffer from higher friction losses and require special materials and lubricants. Engineers must weigh these trade-offs when selecting gear types for specific applications. Real-world testing is essential to validate theoretical models and simulations. Torque sensors, dynamometers, and high-speed cameras are used to measure performance under various conditions. These tests help identify potential issues such as misalignment, excessive wear, or unexpected vibration. Data collected from testing is used to refine gear designs, select appropriate materials, and optimize lubrication strategies. Monitoring systems can be integrated into gearboxes to track temperature, vibration, and torque in real time, allowing for predictive maintenance and reducing the risk of unexpected failures. In summary, gear ratios are not just mathematical expressions, but practical tools that shape the behavior of mechanical systems. By understanding the interplay between torque, speed, inertia, and efficiency, engineers can design gear systems that meet the precise needs of any application. The next section will explore how different gear materials and manufacturing processes influence these performance characteristics and contribute to the reliability and longevity of modern mechanical systems. Gears are made from a wide variety of materials, and each choice is driven by the intended application, operating environment, mechanical requirements, and cost considerations. The selection of a gear material affects not only the strength and durability of the gear, but also its wear resistance, thermal stability, vibration absorption, noise characteristics, and machinability. One of the most commonly used materials for gears is steel, due to its excellent mechanical properties, including high tensile strength, fatigue resistance, and the ability to be heat-treated for enhanced surface hardness. Steel gears are found in applications ranging from automotive transmissions to industrial machinery and aerospace components. Within the family of steels, different alloying elements such as chromium, nickel, molybdenum, and manganese are used to tailor specific performance traits. For instance, carburized steel is commonly employed for gears requiring a hard outer surface and a tough, ductile core. The carburization process introduces carbon to the surface layer of the steel, followed by heat treatment, which creates a hardened shell capable of resisting wear while maintaining a tough interior to absorb shock loads. Stainless steel gears are used in environments where corrosion resistance is critical, such as marine applications, food processing equipment, and medical devices. Although stainless steels typically have lower hardness compared to carburized steels, their ability to withstand moisture, chemicals, and extreme temperatures makes them suitable for demanding environments. Another material widely used in gear manufacturing is cast iron. Cast iron gears are often employed in low to moderate load applications where damping of vibrations and noise is beneficial. The graphite structure of cast iron provides excellent machinability and inherent damping capacity, which helps reduce operational noise. However, cast iron is brittle and may not be suitable for applications involving high shock loads or dynamic stresses. Non-ferrous metals, such as bronze and brass, are also used for gear production, especially in worm gears and applications requiring low friction and good wear resistance. Bronze gears are favored in situations involving high contact stress and sliding action because the material forms a lubricating oxide layer that reduces friction and wear. Additionally, bronze exhibits good corrosion resistance and is commonly found in marine environments, pumps, and gearboxes, subjected to high loads and continuous operation. Brass gears, while softer than bronze, are easy to machine and provide adequate performance in light-duty applications, such as instrumentation and precision devices. Aluminum is another material used for gears, particularly in lightweight and low-load applications, where weight reduction is a priority. Aluminum gears offer excellent corrosion resistance, ease of fabrication, and compatibility with other aluminum components. However, they suffer from lower strength and wear resistance compared to steel or bronze, which limits their use in high-stress or high-torque systems. Plastics are increasingly employed in gear manufacturing, especially in applications requiring quiet operation, low cost, and resistance to moisture or chemicals. Thermoplastics such as nylon, acetal, and polycarbonate are commonly used in consumer electronics, appliances, and automotive interiors. Plastic gears are lightweight, corrosion-resistant, and capable of operating without lubrication in many cases. Reinforced plastic gears which incorporate materials such as glass or carbon fibers, offer improved strength and dimensional stability. However, plastic gears are susceptible to creep under load and may deform over time if not properly supported or cooled. In addition to the base material, surface treatments and coatings play a significant role in gear performance and longevity. One common treatment is nitriding, a process that diffuses nitrogen into the surface of steel gears to form a hard layer that resists wear and scuffing. Nitriding is typically performed at lower temperatures than carburizing, which helps preserve the dimensional stability of finished parts. Another technique is induction hardening, where the gear teeth are selectively heated by electromagnetic induction and then rapidly cooled to create a hardened surface layer. Induction hardening provides localized strength and wear resistance without affecting the core properties of the gear. Phosphate coatings are used to reduce friction and improve lubrication retention, particularly in gears that operate under boundary lubrication conditions. Zinc plating and other anti-corrosion coatings are applied to protect gears from rust and environmental degradation. In high-performance or specialized applications, gears may receive coatings such as titanium nitride, diamond-like carbon, or molybdenum disulfide to enhance surface hardness, reduce friction, and extend service life under extreme conditions. These coatings are often applied using physical vapor deposition or chemical vapor deposition processes that ensure a uniform and adherent layer. Powder metallurgy is another method used in gear production, especially for high-volume manufacturing of small to medium-sized gears. This process involves compacting metal powders into a mold, followed by sintering at high temperature to create a solid part. Powder metallurgy allows precise control over material composition, porosity, and geometry, resulting in cost-effective gears with good mechanical properties and minimal material waste. Composite gears, made by combining different materials such as metal cores with polymer teeth, are used to optimize performance in hybrid systems where weight, noise, and wear resistance must be balanced. Engineers must also consider thermal expansion when selecting gear materials. Different materials expand and contract at different rates in response to temperature changes, which can affect gear alignment, backlash, and meshing accuracy. For high-precision applications such as aerospace or robotics, materials with low thermal expansion coefficients and high dimensional stability are preferred. Environmental conditions such as humidity, salinity, and chemical exposure influence material selection as well. For example, gears used in offshore oil rigs must resist saltwater corrosion, while those in chemical processing plants must withstand acidic or alkaline substances. Ultimately, the material and coating choices for gears are determined by a complex interplay of factors including load, speed, temperature, noise, cost, manufacturability, and environmental exposure. Material selection is often guided by standards and testing protocols to ensure reliability and compliance with industry requirements. By understanding the properties and trade-offs associated with each material, engineers can design gear systems that meet the rigorous demands of modern machinery and ensure long-term performance and safety. The next section will explore how manufacturing processes such as hobbing, broaching, shaping, and grinding contribute to the accuracy, surface finish, and functionality of gear teeth, and how these methods are selected and optimized for different production volumes and quality requirements. The manufacturing processes used to produce gears play a critical role in determining the final performance, accuracy, and lifespan of the gear system. These processes must achieve high precision in tooth geometry, surface finish, and dimensional consistency to ensure proper meshing, minimal noise, and efficient power transmission. The most widely used gear manufacturing process is gear hobbing, which is a highly versatile and efficient method for producing external spur and helical gears. In gear hobbing, a specialized cutting tool called a hob rotates in synchronization with the gear blank while gradually cutting the teeth as the blank spins. The hob has a helical cutting edge that continuously generates the gear profile through a rolling motion, resulting in accurate and repeatable gear teeth. Gear hobbing is favored for medium to high production volumes due to its speed and ability to create complex tooth forms. However, hobbing cannot be used for internal gears or certain specialty profiles, which require alternative methods. One such method is gear shaping, which uses a reciprocating cutter that mimics the gear tooth profile. The cutter and gear blank rotate together in a coordinated fashion, and the cutter reciprocates vertically to progressively carve the teeth. Gear shaping is especially useful for internal gears, splines, and gears with shoulder constraints or complex geometries. Although slower than hobbing, shaping offers greater flexibility in terms of gear type and configuration. Another important manufacturing technique is gear broaching, which uses a long, multi-tooth tool to cut the entire gear profile in a single pass. The broach is pulled or pushed through the gear blank, with each successive tooth removing more material. Gear broaching is often used for internal gears in high-volume production where consistency and speed are essential. The broach itself is expensive and requires precise alignment, making the process cost-effective only for large production runs with standardized gear sizes. For gears that require exceptional accuracy and surface finish, gear grinding is employed as a finishing process. Gear grinding removes small amounts of material using abrasive wheels or stones, resulting in extremely smooth surfaces and precise tooth geometry. This method is essential for high-performance gears used in aerospace, automotive transmissions, and precision machinery. Grinding eliminates heat-affected zones, improves load distribution, and reduces the risk of gear noise or failure. Although time-consuming and expensive, gear grinding is indispensable in applications where quality and reliability are paramount. Another finishing technique is gear lapping, where two mating gears are run together with an abrasive slurry to remove imperfections and improve tooth contact. Gear lapping is used to enhance the meshing characteristics of paired gears and is particularly useful in applications where smooth operation and quiet performance are required. This process is often applied to gears in aircraft systems, instrument drives, and other sensitive equipment. In addition to cutting and grinding methods, gears can also be manufactured through molding and casting processes. Plastic gears are typically produced using injection molding, where molten plastic is injected into a steel mold and rapidly cooled to form the gear shape. Injection molding allows for high-speed production of complex geometries and is widely used in consumer electronics, appliances, and lightweight mechanical assemblies. The molds used in injection molding are expensive to produce but can yield millions of identical parts with tight tolerances and excellent surface finish. For metal gears, investment casting and die casting are employed for producing near net-shape parts that require minimal machining. These methods are suitable for large gears, specialty alloys, or low-volume production, where traditional cutting methods would be inefficient. Forging is another technique used to manufacture strong and durable gears. In the forging process, metal blanks are heated and shaped under high pressure using dies. Forged gears have excellent grain structure, high strength, and good fatigue resistance, making them suitable for heavy-duty applications such as agricultural equipment, trucks, and industrial gearboxes. After forging, gears are typically machined and heat-treated to achieve final dimensions and hardness. Additive manufacturing, or 3D printing, is an emerging technology in gear production, particularly for prototyping and low-volume custom parts. Metal additive manufacturing techniques, such as selective laser melting and electron beam melting, can produce complex gear shapes with internal features that would be difficult or impossible to achieve using traditional methods. While additive manufacturing currently lacks the surface finish and material consistency of conventional processes, it holds promise for future gear production in specialized applications. Heat treatment is a critical step in gear manufacturing to enhance hardness, wear resistance, and strength. Common heat treatment methods include carburizing, nitriding, induction hardening, and quenching and tempering. Carburizing introduces carbon into the surface of low-carbon steel gears to create a hard outer layer while maintaining a tough core. Nitriding diffuses nitrogen into the surface to form hard nitrides without requiring quenching. Induction hardening selectively hardens gear teeth by using localized heating, followed by rapid cooling. Each heat treatment process must be carefully controlled to achieve the desired balance of hardness, toughness, and dimensional stability. Metrology and inspection are essential throughout the manufacturing process to ensure gear quality. Advanced measuring tools, such as coordinate measuring machines, gear analyzers, and optical scanners, are used to verify tooth geometry, pitch accuracy, runout, and surface finish. Inspection data is used to guide process adjustments, identify defects, and ensure compliance with industry standards. Process control and quality assurance are critical in high-performance applications, where gear failure can result in catastrophic consequences. Manufacturing also includes finishing operations, such as deburring, shot peening, and coating. Deburring removes sharp edges and residual material that could interfere with gear operation. Shot peening introduces compressive stresses into the gear surface to improve fatigue life. Coatings such as anti-corrosion layers, lubricants, and wear-resistant films enhance gear durability and performance. Assembly considerations such as keyways, splines, and press fits must also be accounted for in gear design and production. Gear manufacturing is a complex and multidisciplinary process that requires expertise in materials, science, machining, thermal processing, and quality control. Each gear must meet strict tolerances to function reliably in its intended environment. Advances in machine tools, computer-aided design, and automation have significantly improved the precision, efficiency, and repeatability of gear manufacturing. However, the choice of process must always align with the specific performance requirements, production volume, and cost constraints of the application. Understanding the full spectrum of gear manufacturing methods allows engineers to select the optimal approach for each design challenge, ensuring that the gears produced are not only functional, but also economical, reliable, and durable in real-world conditions. The materials used in the production of gears have a profound influence on their performance, longevity, and suitability for specific applications. Selecting the right material involves balancing a range of mechanical properties such as strength, hardness, ductility, toughness, and resistance to wear and corrosion. Steel is by far the most commonly used material for gears because of its excellent combination of strength, machinability, and heat treatability. Carbon steel is frequently used for low to medium load gears and is often chosen when cost is a significant factor. It offers good toughness and can be surface hardened through heat treatment to improve wear resistance. Alloy steels, which incorporate elements such as chromium, molybdenum, and nickel, provide enhanced strength and toughness and are widely used in high-performance gears. These steels can undergo various heat treatments to develop specific properties such as core toughness and surface hardness. Stainless steel is selected for gears that must resist corrosion in humid or chemically aggressive environments. While stainless steels are more difficult to machine and generally have lower hardness than carbon and alloy steels, their corrosion resistance makes them ideal for food processing equipment, medical devices, and marine applications. Cast iron is another material used in gear production, especially for applications where vibration damping and wear resistance are important. Grey cast iron, which contains flake graphite, provides good damping characteristics and is used in large industrial gears and gear housings. Ductile iron, with its spheroidal graphite structure, offers improved toughness and is used in applications that require both strength and impact resistance. For gears operating under extreme loads or requiring high strength-to-weight ratios, non-ferrous metals such as bronze, brass, and aluminum alloys may be employed. Bronze gears are commonly used in worm gear applications because of their excellent wear resistance and ability to operate with minimal lubrication. Brass is often chosen for light-duty gears in clocks, instruments, and decorative applications due to its good machinability and corrosion resistance. Aluminum gears are lightweight and provide good thermal conductivity, making them suitable for applications where weight is a critical consideration, though their lower strength limits their use in high-load situations. Plastic materials are increasingly used in gear production for applications that require quiet operation, corrosion resistance, and low weight. Common gear plastics include acetal, nylon, and polycarbonate. Acetal offers excellent dimensional stability, low friction, and good fatigue resistance, making it suitable for precision gears in printers, cameras, and consumer electronics. Nylon is valued for its toughness and self-lubricating properties, though it is more susceptible to moisture absorption, which can affect its dimensions. Polycarbonate provides high impact resistance and is used in gears that may be subjected to shock loading. Composite materials, which combine a polymer matrix with reinforcing fibers or fillers, are used in demanding applications that require a balance of strength, weight, and environmental resistance. Fiberglass reinforced nylon gears, for instance, offer improved stiffness and dimensional stability over unfilled nylon. In some aerospace and high-performance automotive applications, carbon fiber composites are used to produce lightweight gears with high strength and low inertia. Coatings and surface treatments are applied to gear materials to enhance performance, protect against wear and corrosion, and improve lubrication characteristics. One common treatment is carburizing, where carbon is diffused into the surface of low-carbon steel gears to create a hard, wear-resistant case while maintaining a tough and ductile core. This treatment is often followed by quenching and tempering to develop the desired hardness profile. Nitriding introduces nitrogen into the surface of alloy steel gears, forming hard nitrides that increase wear resistance and fatigue strength without the need for quenching. Nitrided gears exhibit excellent dimensional stability and are commonly used in aerospace and automotive applications. Phosphating is a surface treatment that applies a layer of phosphate crystals to steel gears to enhance corrosion resistance and serve as a base for lubricants. It is often used on gears that will be stored for extended periods or exposed to mild corrosive environments. Black oxide is another treatment that provides mild corrosion protection and an aesthetically pleasing black finish. It is often used for gears in consumer products and instruments. Electroplating can deposit layers of metal such as zinc, nickel, or chromium onto gear surfaces to improve corrosion resistance and surface hardness. Zinc plating provides sacrificial protection against rust and is common in gears used in outdoor equipment. Nickel plating offers a hard, corrosion-resistant finish suitable for gears in chemical processing and food handling environments. Chromium plating enhances wear resistance and provides a mirror-like finish, though it is more expensive and typically reserved for high-end or decorative applications. Solid film lubricants and dry coatings such as molybdenum disulfide and polytetrafluoroethylene can be applied to reduce friction and improve wear performance in low lubrication environments. These coatings are often used in space or vacuum applications where traditional lubricants are not feasible. Shot peening is a mechanical surface treatment that bombards the gear surface with small spherical media to introduce compressive residual stresses. These stresses increase fatigue life and resistance to crack initiation, making shot peening an essential process for gears operating under cyclic or shock loads. The choice of material and coating must be matched to the gear's application, load conditions, operating environment, and desired lifespan. In safety-critical systems, such as aircraft or medical devices, extensive testing and certification of materials and treatments are required to ensure consistent performance and reliability. Advances in material science continue to expand the range of available options for gear designers. High-strength steels with improved fatigue properties, wear-resistant alloys, and new plastic composites are enabling gears to perform under more demanding conditions than ever before. Emerging technologies, such as surface engineering, nanostructured coatings, and functionally graded materials, hold the promise of further improving gear performance in the future. Understanding the interplay between base materials, manufacturing processes, and surface treatments is essential for optimizing gear design and ensuring that the final product meets all functional requirements. A well-chosen material and coating can dramatically extend the life of a gear, reduce maintenance intervals, and improve overall system efficiency. Engineers must consider not only the mechanical properties, but also the economic and environmental implications of their material choices, as sustainability and recyclability become increasingly important in modern engineering practice. Lubrication plays an essential role in the performance, durability, and efficiency of gear systems across all mechanical applications. Gears operate under conditions of high contact pressure, friction, and heat generation due to the interaction between their mating surfaces. Without proper lubrication, these systems would quickly suffer from excessive wear, elevated temperatures, and ultimately, mechanical failure. The function of gear lubrication extends beyond merely reducing friction. It also forms a thin film between gear teeth that helps distribute the load more evenly, prevent direct metal-to-metal contact, and protect against corrosion and contamination. In highly loaded gear applications, such as those found in industrial machinery, automotive transmissions, and aerospace systems, lubrication determines not only how smoothly the gears mesh, but also how long they can function before needing maintenance or replacement. There are several types of lubricants used in gear systems, including oils, greases, and solid lubricants. Each type is selected based on specific performance requirements, operating temperatures, environmental conditions, and the nature of the gear contacts. Gear oils, for instance, are common in enclosed gearboxes and offer excellent thermal stability, viscosity control, and oxidation resistance. These oils may be mineral-based or synthetic, with synthetic oils generally offering superior performance at extreme temperatures. Additives such as anti-wear agents, corrosion inhibitors, and extreme pressure compounds are often blended into the oil to enhance its protective capabilities. Grease, which is a semi-solid lubricant composed of base oil and thickener, is frequently used in open gears or in applications where leakage might be problematic. Grease provides a longer-lasting lubricating film and can operate in conditions where oil would drain away or evaporate. Solid lubricants such as graphite or molybdenum disulfide are reserved for specialized situations where conventional lubricants cannot function, such as vacuum environments or extremely high temperatures. One of the key performance metrics in lubricated gear systems is the coefficient of friction, which affects how efficiently energy is transmitted through the gear train. Lower friction means less energy is lost to heat and more is delivered as useful mechanical power. Proper lubrication helps achieve this by minimizing sliding resistance between gear teeth during meshing. However, if the lubricant film is too thin, it may break down under pressure, leading to boundary lubrication conditions in which asperities on the gear surfaces make contact. This causes localized wear, scuffing, and pitting that reduce gear life. Conversely, if the lubricant is too thick or viscous, it can increase drag and reduce mechanical efficiency. Therefore, selecting the correct viscosity grade and maintaining it within the appropriate temperature range is vital to optimizing performance. Lubrication also affects thermal management in gear systems. As gears rotate and generate heat through friction and compression, the lubricant carries away a portion of this thermal energy and transfers it to the surrounding housing, where it is dissipated through conduction or cooling systems. In high-performance gearboxes, such as those used in racing or aerospace applications, dedicated oil circulation systems are often employed. These systems include pumps, filters, and heat exchangers that maintain optimal oil cleanliness, temperature, and pressure. Thermal stability of the lubricant is critical because high temperatures accelerate chemical degradation, forming sludge, varnish, and acids that compromise the lubricating film. Proper filtration and maintenance schedules help mitigate these risks and extend both lubricant and gear lifespan. The efficiency of gear systems is closely tied to lubrication regimes, which are typically classified into boundary, mixed, and hydrodynamic lubrication. Boundary lubrication occurs when the lubricant film is insufficient to separate the surfaces completely, and additive chemistry plays a dominant role. Mixed lubrication is a transitional phase where partial fluid film and surface contact coexist. Hydrodynamic or elasto-hydrodynamic lubrication represents the ideal state where a full fluid film supports the load, eliminating direct surface contact. The design of gear teeth, surface finish, speed of operation, and load all influence which lubrication regime predominates in a given application. Surface roughness is another critical factor. Smoother surfaces allow for better lubricant film formation and reduce asperity contact. However, overly polished surfaces can also hinder oil retention. Therefore, gear surfaces are often engineered with a balance between smoothness and microtexture to optimize oil adhesion and film stability. Gear engineers must consider not only the type of lubricant, but also the method of delivery. Splash lubrication is commonly used in simpler gearboxes, where rotating gears fling oil onto other components. Forced circulation systems, as mentioned earlier, are used in complex setups. Mist lubrication, where oil is atomized and delivered as a fine spray, is utilized in some high-speed or sealed environments. Each method has trade-offs in terms of cost, complexity, and reliability. Another important consideration is the compatibility of lubricant materials with gear metals, seals, and surrounding components. Incompatible oils can cause swelling, degradation, or chemical attack, particularly on synthetic materials used in seals or bushings. Manufacturers typically test lubricant formulations extensively to ensure chemical stability and long-term compatibility with a range of materials. Environmental and sustainability factors are also increasingly influencing lubricant selection. The push for biodegradable lubricants, reduced oil consumption, and extended drain intervals is driven by both regulatory requirements and corporate environmental goals. Synthetic esters and other environmentally friendly base stocks are being developed to meet these needs without compromising performance. In conclusion, lubrication is not a peripheral concern in gear engineering, but a central design parameter that directly affects performance, reliability, and energy efficiency. It involves a careful balance of material science, fluid dynamics, thermal management, and mechanical engineering. The science of lubrication has advanced considerably, enabling gear systems to operate at higher loads, speeds, and efficiencies than ever before. Yet even the best designed gears cannot perform optimally without the correct lubricant applied in the right manner. Engineers must continue to develop and apply innovative lubrication strategies to meet the evolving demands of modern machinery and sustainable engineering practices. Gears play a fundamental role in the operation of countless mechanical systems across industries, ranging from transportation and manufacturing to robotics and power generation. Each type of gear is designed with specific mechanical functions in mind, and their individual characteristics allow engineers to select the most efficient and reliable configuration for a given application. Spur gears are among the most commonly used gears and are characterized by their straight teeth, which are mounted on parallel shafts. They are simple to manufacture and efficient under moderate loads and speeds. These gears are typically found in applications where noise is not a primary concern, such as industrial machinery, conveyor systems, and mechanical clocks. Their straightforward geometry allows for consistent meshing and low production costs, making them ideal for general-purpose power transmission. Helical gears differ from spur gears in that their teeth are cut at an angle to the axis of rotation, which allows for more gradual engagement of the teeth and thus quieter and smoother operation. This feature makes them well suited for high-speed and high-load applications, such as automotive transmissions and large-scale industrial equipment. Their axial thrust, however, necessitates the use of thrust bearings and more robust housings. Bevel gears are designed to transmit power between intersecting shafts, typically at right angles. Their conical geometry enables the redirection of motion and torque, and they are commonly found in differential drives, where torque must be split between two axles. Bevel gears are also used in hand drills and marine applications, where compact redirection of motion is necessary. Worm gears provide very high reduction ratios and are distinguished by a screw-like worm that engages with a helical gear. This setup allows for high torque transmission and is inherently non-reversible, which means that the gear cannot drive the worm. This self-locking property is especially valuable in applications such as hoists, elevators, and conveyors, where holding position is critical. However, worm gears tend to be less efficient due to the sliding contact between the worm and the gear, which generates heat and leads to wear. Planetary gear systems, also known as epicyclic gear trains, consist of a central sun gear orbiting planet gears, and a surrounding ring gear. These systems are highly compact and capable of delivering high torque density and multiple gear ratios within a small footprint. Planetary gears are widely used in automatic transmissions, electric screwdrivers, and aerospace applications due to their efficiency and load-sharing capabilities. Rack and pinion systems translate rotational motion into linear motion and are commonly used in automotive steering mechanisms and CNC machines. The pinion engages with a linear gear or rack, allowing precise control of position along a straight path. Hypoid gears are a variation of bevel gears where the axes of the shafts do not intersect. This configuration is frequently found in automotive rear axles due to its ability to handle higher torque loads and offer smoother operation. Spiral bevel gears are similar, but use curved teeth to further enhance smoothness and load distribution. In heavy-duty applications, such as mining construction and marine propulsion systems, engineers often rely on custom gearboxes that combine multiple gear types to achieve desired torque speed and spatial arrangements. These gearboxes are meticulously engineered to balance performance, durability, and maintainability, often incorporating lubrication systems and thermal management features. In robotics and automation, gears must provide not only mechanical efficiency, but also precision. Harmonic drive gears are used extensively in robotic joints due to their zero backlash, high reduction ratio, and compact size. They rely on a flexible spline and elliptical wave generator to achieve smooth and precise motion control. Timing gears and timing belts are essential in engines and synchronized machinery, where the relative position of rotating components must be precisely maintained. These systems ensure accurate timing in combustion engines and production lines. Gears also play a critical role in wind turbines, where the low-speed rotation of the rotor blades must be converted into high-speed rotation for electrical generation. Gearboxes in these systems must withstand variable loads, extreme environmental conditions, and operate reliably over long periods without frequent maintenance. In aerospace engineering, weight constraints and reliability requirements dictate the use of lightweight, high-strength gear materials and designs. Aircraft landing gear actuators, flight control systems, and jet engines all utilize gears engineered for minimal weight and maximum performance. High-speed rail systems employ gear systems to manage power delivery from electric motors to drive wheels, optimizing acceleration and deceleration while minimizing noise and mechanical wear. In medical equipment, such as surgical robots and diagnostic devices, precision, miniaturized gears enable controlled movement and manipulation, often under sterile or constrained conditions. Each gear application must consider factors such as torque requirements, speed ratio, alignment, space constraints, and operating environment. Engineers must also account for noise, vibration, and harshness to ensure long-term reliability and user comfort. The materials selected for gear manufacture depend on the application's load, thermal, and wear requirements, and may include hardened steels, polymers, composites, or even specialized ceramics. Gear maintenance strategies vary widely based on the application, from sealed-for-life gearboxes in consumer electronics to serviceable industrial reducers with replaceable components and lubrication systems. As gear applications continue to evolve with the rise of electrification, autonomous systems, and digital manufacturing, the demands placed on gear systems grow ever more complex. Nonetheless, the underlying principles of gear operation remain rooted in centuries-old mechanical understanding, adapted and enhanced through modern engineering. The wide range of gear types available ensures that for nearly every mechanical challenge, there exists an optimal gearing solution engineered to meet the specific needs of performance, reliability, and efficiency. When analyzing the operation of gear systems in engineering contexts, it is critical to consider not only their ability to transmit motion and change speed or torque, but also their efficiency in doing so. Gear efficiency is a measure of how effectively a gear system transfers power from the input shaft to the output shaft without unnecessary losses. These losses typically manifest as heat generated through friction, noise produced by vibration, and imperfect engagement, and wear on the tooth surfaces due to repeated contact under load. Each gear type carries inherent mechanical characteristics that influence its efficiency and behavior under various operating conditions. Spur gears, with their simple tooth geometry and parallel shaft configuration, generally exhibit high efficiency, often exceeding 95% in well-lubricated systems. Their straightforward engagement produces relatively low sliding friction, though the sudden impact between meshing teeth can produce noise and vibration. Helical gears offer smoother engagement due to the angled teeth and gradual meshing process, which reduces noise but introduces axial thrust and increased sliding contact. This sliding contact leads to higher frictional losses and slightly reduced efficiency, typically ranging between 90 and 95%, depending on load and lubrication. Worm gears operate based on a screw-like worm that meshes with a gear at a 90-degree angle, producing significant sliding between the contact surfaces. This sliding interaction results in efficiency losses that can reduce overall performance to below 50% in some cases, especially when operating under high loads without proper lubrication. Despite this drawback, the worm gear's inherent self-locking characteristic offers mechanical advantages in specific scenarios where backdriving must be prevented. Bevel gears and hypoid gears, designed to transmit power between intersecting or offset shafts, introduce additional complexities in tooth geometry that contribute to variable efficiency. Bevel gears typically operate at 70 to 95% efficiency, depending on tooth type, alignment, and lubrication. Hypoid gears, often used in automotive applications, involve considerable sliding motion and tend to be less efficient than pure bevel gears. Though advances in gear surface treatments and synthetic lubricants have helped mitigate these losses, mechanical advantage in gear systems is closely tied to gear ratios, which define the relative sizes and rotational speeds of the input and output gears. A higher gear ratio implies a greater torque multiplication at the cost of reduced speed. The mechanical advantage can be calculated by dividing the output torque by the input torque, and it directly influences how much force the gear system can deliver to the load. For example, in applications requiring heavy lifting or slow, precise movement, high gear ratios are preferred to maximize torque, even at the expense of speed. This trade-off between speed and torque is governed by the conservation of energy principle, meaning the power at the input equals the power at the output minus losses. As gear systems scale up for industrial machinery, the importance of maintaining high efficiency becomes even more critical. Energy losses due to friction and heat can compound rapidly in large mechanical systems, leading to wasted power, increased operating costs, and accelerated wear of components. Engineers mitigate these losses through careful material selection, surface treatments, like case hardening or nitriding, and the application of advanced lubricants that reduce friction and wear. Synthetic lubricants, in particular, are engineered to maintain consistent viscosity across a wide temperature range, ensuring optimal gear engagement and thermal control. In addition to materials and lubrication, gear tooth geometry plays a significant role in determining efficiency and mechanical advantage. Involute tooth profiles, the most common shape used in modern gears, provide consistent transmission of motion and self-correcting meshing characteristics. These profiles allow for slight misalignment between shafts without compromising gear performance, reducing the risk of localized stress and wear. The gear backlash, or the small clearance between mating gear teeth, is another critical factor that affects both mechanical performance and efficiency. Too much backlash leads to imprecise motion and increased noise, while too little can cause binding and accelerated wear. Properly setting backlash requires precise machining and alignment during assembly, and is often adjusted manually during maintenance or tuning. Another important consideration is the load distribution across gear teeth. Ideally, the contact should be evenly spread across the entire width of the tooth to distribute forces and minimize localized pressure. In reality, manufacturing imperfections, shaft deflection, or misalignment can cause uneven loading, leading to increased wear and reduced efficiency. Engineers use tools such as finite element analysis and tooth contact analysis to predict and compensate for these issues in the design phase. Thermal expansion, lubrication breakdown, and contamination can all further reduce efficiency over time. Therefore, gear systems are often equipped with temperature sensors, lubrication monitoring systems, and vibration analysis tools to detect early signs of inefficiency and wear. These predictive maintenance strategies help ensure consistent performance and reduce the risk of unexpected failure. In high-speed gear systems, such as those found in aerospace or automotive applications, dynamic balancing and vibration damping become essential to preserving efficiency and mechanical integrity. Imbalances in gear mass or eccentric motion can introduce unwanted harmonics, resulting in energy loss through vibration and noise. Engineers address these challenges through careful design of gear housing, precision manufacturing, and the use of dampers or isolators. Finally, the integration of electronics and digital monitoring systems has further enhanced our ability to manage and optimize gear efficiency. Sensor feedback, real-time performance tracking, and algorithmic control allow for adjustments to operating conditions that maintain optimal efficiency across a wide range of loads and environments. Gear efficiency is thus not a static property, but a dynamic characteristic influenced by numerous interrelated variables, including speed, load, lubrication, material, geometry, and maintenance. Through careful design, continual monitoring, and adherence to best engineering practices, gear systems can be made to operate with remarkable precision and efficiency, delivering the necessary mechanical advantage with minimal losses across countless applications. Gear ratios play a crucial role in nearly every branch of mechanical engineering where motion, torque, or power needs to be transferred between mechanical components. These ratios, which represent the relationship between the number of teeth on two meshing gears, govern how fast and how forcefully an output shaft rotates in response to the input shaft. In real-world engineering applications, gear ratios are selected with great care to balance the needs for speed, power, precision, efficiency, and mechanical durability. One of the most familiar examples of gear ratio application is found in the automotive transmission system. Here, gear ratios are used to match the engine's high speed, low torque output to the wheel's need for varying levels of torque and speed. In a low gear, a high gear ratio allows the engine to multiply torque significantly, making it easier for a vehicle to accelerate from a stop or climb a hill. As the vehicle gains speed, the transmission shifts to higher gears with lower ratios, reducing engine RPM and improving fuel efficiency. Manual and automatic transmissions both use this principle, though automatic systems use complex planetary gear sets and hydraulic or electronic controls to automate ratio changes. In electric vehicles, although transmissions are often simplified due to the electric motor's broad torque band, gear ratios are still essential for final drive and motor optimization. Beyond automobiles, bicycles provide another intuitive illustration of gear ratios. A cyclist switches between gears to make pedaling easier on inclines or faster on flat terrain. A smaller front chainring and larger rear sprocket create a high gear ratio that increases torque at the expense of speed, while a larger front chainring and smaller rear sprocket allow for greater speed but require more pedaling force. This balance of mechanical advantage and cadence illustrates the trade-offs inherent in all gear-driven systems. Industrial machinery offers countless examples of gear ratio applications. Conveyor systems use gear reducers to ensure motors deliver appropriate torque for moving heavy loads at controlled speeds. In robotic arms, different joints may require varying gear ratios, depending on whether precision, speed, or strength is prioritized. High gear ratios are used at joints that must lift heavy payloads with accuracy, while lower ratios may be acceptable where speed is more important than force. The gearboxes in wind turbines represent a specialized case where low-speed rotation from the turbine blades must be increased to high-speed rotation to drive electrical generators efficiently. This often involves gear ratios exceeding 100:1, accomplished using multiple gear stages. Any inefficiency in this process can result in significant energy losses, so gear materials, lubrication, and cooling systems are carefully designed to maintain performance over years of operation under variable loads and weather conditions. Aerospace systems also rely heavily on precision gear ratios, particularly in control surfaces and actuation systems. For example, when adjusting the position of ailerons, elevators, or flaps, actuators must deliver controlled motion under aerodynamic loads with absolute precision. Here, high-ratio gearboxes enable electric or hydraulic motors to produce fine movements while resisting wind forces. Similarly, the deployment of landing gear, cargo bay doors, and satellite antennae involve gear systems where speed must be sacrificed for torque and positional control. In marine engineering, propulsion systems frequently use gearboxes to reduce the high rotational speed of marine engines to match the lower optimal speed of propeller shafts. This reduction not only improves thrust efficiency, but also reduces cavitation and noise. In some cases, marine gearboxes include reverse gears and hydraulic clutches to accommodate maneuvering. In power tools and household appliances, gear ratios are used to adapt high-speed electric motor output to usable torque levels for specific functions. A hand drill, for instance, incorporates planetary gears to deliver sufficient torque at controllable speeds for for drilling or driving screws. Food mixers use gear systems to adjust rotation speeds depending on whether the user wants to knead dough or whip cream. These small-scale implementations follow the same principles as large industrial machines, though the materials and tolerances are adapted to domestic use. In railway systems, traction motors use gearboxes to convert high-speed electric motor rotation into the low-speed, high-torque motion necessary to move heavy train cars. The ratio is selected based on the balance between acceleration, top speed, and efficiency. High-speed trains require different gear strategies than freight locomotives due to their differing priorities in speed and load capacity. In elevators and escalators, gear systems ensure controlled and safe movement of people across vertical and inclined surfaces. High gear ratios provide the torque needed to lift elevator cabs while minimizing power consumption. Gearbox design in such applications must also account for safety redundancies and smooth acceleration and deceleration to avoid discomfort. In the energy sector, gearboxes are found in oil rigs, drilling equipment, and hydraulic fracturing systems where immense forces are required under hostile conditions. High torque and precise control are necessary for both safety and efficiency. Often, gearboxes are enclosed in protective housings and cooled using specialized fluids to maintain operation under high pressure and temperature. Even in entertainment and media production, gear ratios play a role. Camera gimbals use miniature gears to stabilize footage and allow for controlled pans and tilts. Stage equipment, such as lighting rigs and retractable platforms, often rely on gear systems to deliver consistent and quiet movement. In each of these fields, the exact gear ratio selected depends on a careful analysis of load characteristics, speed requirements, energy sources, desired motion profiles, and cost constraints. Engineers use simulation software to model gear behavior under various conditions, and prototyping ensures that theoretical gear ratios function as intended in practice. Improper gear ratio selection can lead to underperformance, excessive wear, overheating, or failure, so precise specification is critical. In summary, the use of gear ratios in real-world engineering is both ubiquitous and essential. From the smallest mechanisms in watches and cameras to massive installations in power plants and marine propulsion systems, gear ratios enable the efficient and controlled transfer of mechanical energy. Their presence is often hidden behind covers and housings, but their impact is profound. The correct selection and implementation of gear ratios is a cornerstone of mechanical design and a testament to the enduring power of simple mechanical principles applied with precision.